Now, in this video, we're going to talk about the characteristics of the Pearson Chi-squared statistic and how to make statistical inference and how to draw a conclusion. Now, consider a simple simulation study to assess the characteristics of the test statistic. We consider k equals to 2, which is a coin tossing experiment. And the null hypothesis is that the coin is actually a fair coin, such that the proportion of getting a head in each trial equals to 0.5, and the proportion of getting a tail equals to 0.5. We simply, when k equals to 2, we simply specify the two proportions, even though we specify the proportion of getting a head is equivalent to setting the proportion of getting a tail as well. And the alternative hypothesis is that the coin is a loaded coin such that the proportion of getting a tail is not equal to 0.5. And the simple experiment is that the coin is tossed 1,000 times in an experiment, and the number of heads and tails are recorded. And the chi-square statistic is then calculated based on the experimental data, and steps 1 and 2 are repeated 10,000 times in this simulation. From the Excel file, we have the first data set, O1 equals to 490, O2 equals to 510, and so on. And this is and therefore the test statistic is 0.4 in the first data set. In the second data set, we have a perfect situation with O1 equals to 500, O2 equals to 500. And the test statistic equals to 0, and so on. And we repeated the experiment 10,000 times, such that we will have 10,000 such test statistics. In the first trial, we generate the data under the null hypothesis, and then we plot the 10,000, the histogram of the 10,000 test statistics, and we end up with this empirical distribution. And as mentioned earlier, that the chi-square statistic is known to follow a chi-square distribution. Okay, and for the one-way classification problem, the chi-square distribution has degrees of freedom k-1. And when we compare with the chi-square distribution as shown in the red curve, you can see that the empirical distribution agree closely with the theoretical distribution, which is a chi-square 1 distribution. In the second set of simulation, we generate the data under the alternative hypothesis with the probability of getting a head equals to 0.45 instead of 0.5. And the distribution is plot as the pink histogram in parallel to the null distribution, which is the one under the purple. The purple one is the distribution under the null, and the pink one is the distribution under the alternative, that the proportion of getting a head equals to 0.45. And you can see easily under the alternative hypothesis, the value of the test statistics tends to be very, very, very large. Okay, and as large as 20 or even 30. And the third set of simulation is to generate the data under the alternative hypothesis with the probability of getting a head even further away from the null hypothesized value of 0.5, which is we set pH equals to 0.4, and the empirical distribution is plotted in the diagram with the green color as well. So you can see the three distributions under the three hypotheses are actually very different, with the hypothesized value, with the true value of the proportion further away from the hypothesized value of 0.4. You can see that the value of the test statistic will tend to be much, much larger. So that echo with the argument that a large value of the test statistic is in favor of the alternative hypothesis. To give you an example, according to a geneticist theory, a crossing of red and white snapdragons should produce offspring that are 25% red, 50% pink, and 25% white in the ratio of 1 to 2 to 1. An experiment conducted to test the theory produces 32 red, 76 pink, and 36 white offspring in 144 crossings. The question is, do the data provide sufficient evidence to contradict the geneticist theory and use alpha equals to 0.05, and in this case we have K equals to 3 classes, and the null hypothesis, P1 is the proportion of red equals to a quarter, and P2 is the proportion of pink equals to 1/2, and P3 the proportion of white equals to a quarter, while the alternative hypothesis is that the null hypothesis is not true. And here is the data. We have O1 equals to 32, O2 equals to 76, and O3 equals to 36. And the expected frequency under the null hypothesis would be 36, which is n multiplied by the hypothesized value a quarter. 144 multiplied by a quarter equals to 36, and O2 is n multiplied by P2 naught, which is 144 multiplied by 0.5 equals to 72, and E3 equals to 36. And therefore, the tail statistics can be computed easily by substituting the number into the formula to be 2/3. And if you look at the tail statistics, if the OIs agree closely with the EIs for all the I's, then the null hypothesis should be appropriate, and the tail statistic x squared will tend to be small. But if there is a huge discrepancy between the observed frequency and the expected frequency under the null hypothesis, then that means the square of the discrepancy will inflate the value of the tail statistics, and hence a large value of the tail statistics is in favor of the alternative. Now, recall that when n is large, the tail statistic will possess approximately a chi-square distribution with degrees of freedom k-1, where k is the total number of classes. In this case, we have 3 classes, namely red, pink, and white. So k-1 equals to 2. And the chi-square distribution is characterized by the degrees of freedom. And under the null hypothesis, the tail statistic follows approximately a chi-square distribution with degrees of freedom k-1. And this is a plot of the chi-square distribution with different degrees of freedom. And when should we reject the null hypothesis? We will reject the null hypothesis if the tail statistic is large. But how large is large? In general, we let alpha be the level of significance, such that we say alpha equals to 0.05, for example. That means we will leave 5% at the tail area. And if we think that the tail statistic falls in the last 5 percentile, then we will conclude that the tail statistic is large, okay? And we will reject the null hypothesis if the tail statistics fall in the yellow shaded region. And how do we determine the critical value? The critical value. And as a summary, I simply tabulate the first 10 degrees of freedom for several alpha values, namely 0.01, 0.025, and 0.05. And in our last example, if we fix alpha equals to 0.05 and degrees of freedom equals to 2, then the critical value is 5.99. That means if a tail statistic has a value greater than 5.99, then the null hypothesis will be rejected. So hence, for some pre-specified level of significance alpha, the null hypothesis will be rejected if the tail statistic, computed tail statistic, is greater than the quantile from the table. In our last example, we have k equals to 3. That means we have a 2 degrees of freedom and a chi-square distribution with alpha equals to 0.05. The critical value is found to be 5.99. And it is obvious that the tail statistic is only 2/3, which is much smaller than 5.99. So therefore, the null hypothesis is not rejected at the 0.05 level of significance, and we may conclude that the geneticist theory is about correct. And that is the one-way classification problem, or what we call the goodness of fit test. And that means the model is appropriate, proposed by the geneticist is appropriate.